This is the assignment 502.3 impulse and momentum theorem problem set. I'm going to go through the questions starting with number 1. Number 1 says Hyde is driving a 1,870 kilogram car at 20 meters per second before fully applying the brakes 50 meters before a stoplight. If the car stops in 5 seconds, what is the average force applied by the brakes? So again, we're going to start by labeling the information that we know. We have a mass here of 1,870 kilograms. We have an initial velocity of 20 meters per second, and it does describe that as being in the positive direction or forward. We have a final velocity of 0 because it says fully applying the brakes at a stoplight, so he's coming to a stop. We also know the displacement of the vehicle is 50 meters. We have a time of 5 seconds, and it's asking us for force. Okay, so we actually don't need all of these pieces of information. You probably already know that this right here does not show up in any of my equations in this unit. This would show up in a kinematic equation if I needed that, and I don't actually need that here. So that is an extra piece of information that I don't need, but I do have the information to use this equation. F times T equals M times delta V. And so that's what we're going to do. We're going to plug in force times my time here is 5 equals my mass 1,870 times my change in velocity. Now remember, change in velocity, this right here, is VF minus VI. Okay, and look at the question. The final is 0, the initial is 20. My change is negative 20. I don't have to subtract that to know it. If I go from 20 to 0, that is a change of negative 20. Okay, but you can subtract it if you need to. Okay, so 1,870 times negative 20. And then we're going to take that number and divide it by 5 so that we can isolate that F right there. So divide it by 5, and we get a force of 7,480. Okay, and it is negative 7,480, and it will be in units of newtons. Question 2 says, this man is trying to walk on this log without falling over. His friends throw a large rock at him. Should he catch it or let it bounce off of him? We've talked about this previously, but if you have something that you catch, then you're going to have a change in velocity like this problem did from like 20 to 0 or whatever. Okay, but you're going to have a certain change in velocity. Whereas if it bounces, you're no longer going 20 to 0 or whatever the numbers might be. Now you're going 20 to negative 10. Okay, that's a larger change in velocity if it bounces. And if you have a larger change in velocity, you're going to have a larger change in momentum. Remember that equation is mass times change in velocity. If it bounces, this is bigger. If this is bigger, this is bigger. Okay, and a larger change in momentum also means a larger impulse, which means more force, okay, for a given amount of time. Let's look at our options. Catch it, because there will be less change in momentum. Okay, that's what we just talked about. If you catch it, there will be less change in momentum. Let it bounce, because there will be a bigger force. It would absolutely be a bigger force if it bounces, which is why he shouldn't do that. Should he catch it or let it bounce off? He should not do that. You don't want bigger force. Catch it because there will be more change in momentum. That is also true, but again, shouldn't catch it because of that. Okay, you don't want that more change in momentum. Okay, bouncing would not produce more change in momentum. Bouncing does produce this. That's why you don't want to do it. Catching it doesn't do that. Okay, you don't actually have more change in momentum if you catch it. Rather, you would have more change in momentum if you let it bounce, which is why you don't want to do that. You do want to catch it, but this part is not true. That does not happen in this instance. If you catch it, rather, you would have a smaller change in momentum. Question 3, you've seen this before. It says, a 1.5 kilogram ball bounces off of a wall as shown in the image above. The magnitude of force it receives from the wall over time varies according to the graph shown. if the ball strikes the wall with an initial velocity of positive 6.3 meters per second, with what speed does it leave the wall after bouncing? Okay, so obviously in this situation you're going to have a change in velocity, and you can use this formula here, mass times change in velocity, to get your, or in fact, rather, you're going to be using your change in momentum along with your mass to figure this out. Okay, because your change in momentum is equal to your impulse as well. Again, these are mathematically equal to each other. You can calculate impulse from a force time graph, which is what we have here, by finding the area. Okay, so if I look at this graph and I find the area of the triangle, that will give me my impulse. My impulse is also equal to mass times change in velocity, and so I'll be able to use that area and set it equal to the mass 1.5 times delta V and solve for delta V. So let's find the area first. Area of a triangle is 1/2 base times height. This particular triangle, I have a base of 6, I have a height of 4.5. Okay, so 1/2 6 times 4.5, or 3 times 4.5, gives me a impulse, J, of 13.5 Newton seconds, and thus a change of momentum also of 13.5 kilogram meters per second. Okay, however, there's one thing we need to pay attention to, and that is the fact that this says the magnitude of force is shown here. I do need to think for a second about the direction. If this ball is initially traveling positive direction, when it hits the wall, it will now be going in the negative direction. The wall is pushing it in the negative direction, and so my impulse, although I get a positive number because the graph only shows magnitudes, this actually needs to be a negative number for my math. And again, that is because the ball is going in the positive direction and gets pushed in the negative. It's going to change direction. So if this was positive, this is now negative. Okay, and so that's going to matter for my math. So I'm going to use negative 13.5 for my impulse, and thus also for my change in momentum. I'm going to now set this equal to mass times change in velocity, this equation here. The mass, again, is 1.5, and then change in velocity is VF minus VI. So VF minus VI in this problem is 6.3, and this is why that sign matters, because it's minus positive 6.3. Okay, and that needs to be in negative. All right, so from here, I'm going to go ahead and distribute this into the parentheses. So I need 6.3 times 1.5. Okay, and I get 9.45. Okay, so I have over here 1.5 times VF minus 9.45 equals negative 13.5. Again, I'm trying to solve for this final velocity. I'm going to add 9.45 to both sides to cancel it over here. And over here I have 9.45 plus negative or minus 13.5, and I get negative 4.05 equals 1.5 VF. So if I want to solve for VF, I need to divide both sides by 1.5. Divide it by 1.5, and I get a final velocity of negative 2.7. However, again, the question doesn't want velocity, it wants speed. Okay, so when I type in my answer, I'm just typing 2.7. I'm not going to include the direction. My units for that velocity, that speed, are meters per second. By the way, there is a video clip here that can also walk you through the steps of this problem if you want to look at another example. Question 4. The driver of a 1,100 kilogram car moving at 12.7 meters per second applies the brakes for 3.3 seconds. As a result, the car slows to positive 4.7 meters per second. Direction matters. Direction always matters. I'm just reminding you. Find the change in momentum of the car. Find the net force that the brakes applied. So again, let's start by labeling everything. All right, so let's label the information that we have here. So we have mass is 1100. We have an initial velocity of positive 12.7. We have a time of 3.3 seconds. We have a final velocity of positive 4.7 meters per second. And we are looking for change in momentum and force. Okay, so change in momentum, delta P, is equal to mass times change in velocity. It is also equal to force times time because it's equal to impulse. Okay, so in the particular information we have right now, we have information for mass and change in velocity, so we're going to use this first equation right here in order to solve for delta P. Okay, and so we are going to say delta P equals, the mass here is 1100. The change in velocity, again, anytime you're finding change in anything, change in velocity, change in position, change in momentum, whatever, it's always final minus initial. So it's final velocity minus initial velocity. So his final velocity is 4.7, the initial was 12.7, so the change is a negative one. Okay, because you went from this speed to this speed. And again, if you put it into this formula, you'll get a negative number, 4.7 minus 12.7. Okay, so let's go ahead and do that subtraction, 4.7 minus 12.7. Our change in velocity is negative 8, and we're going to multiply that by 1100. And that gives us a change in momentum of negative 8800. So let's go ahead and put that in here. And that's what it means by direction matters. You do have to pay attention to that sign when you're finding the change in velocity. The second question says find the net force whenever the brakes are applied. So again, we just determined our change in momentum, and I've already told you that change in momentum is also equal to impulse, so it's also equal to force times time, which means we can solve for the force because now we have a change in momentum, negative 8800, and we can set it equal to force times time, my time being 3.3 seconds. And so if I want to solve for force, I'm simply going to divide my answer from the previous question, negative 8800, divided by 3.3. And we get this value here, negative 2,666.6 repeating. I'm going to round that to negative 2,666.67. Question number 5. A 33 kilogram file cabinet is at rest. You apply a 30.8 Newton force for 2.7 seconds. Assume no friction. Find the final momentum of the file cabinet and find the acceleration. Okay, so again, we're going to start by labeling the information that we have. So we know that we have a mass of 33 kilograms. We know that it is initially at rest, so the initial velocity is 0 meters per second. We know that we have a force of positive 30.8 newtons. We know that that force is applied for a time of 2.7 seconds. And we want to find the final momentum of the filing cabinet. Okay, now final momentum would be equal to mass times final velocity. Okay, or you could find the change in momentum because your initial momentum is 0. So we either need to find the change in momentum or we need to find the final velocity so that we can determine what our final momentum would be. I'm going to go ahead and I'm going to solve for my final velocity because I feel like that's going to be helpful for me answering the second question, which is to find the acceleration of the cabinet. Although I just realized we could also do that with this F equals ma. So here instead, let's go ahead and do this and say, hey, my change in momentum is equal to force times time, because again, change in momentum is equal to impulse, which is equal to force times time. So we can set those equal to each other, which means all I need to do is 30.8 times 2.7, and that will give me my change in momentum. Okay, so let's go ahead and do that. 30.8 times 2.7 tells me that my change in momentum is 83.16. Okay, so if that's my change in momentum, and my initial momentum was 0, and I know that because my initial velocity is 0, then that means that my final momentum must be equal to 83.16. My acceleration, again, I can find that, and there's more than one way to do this, as I already mentioned, but I can do this. F equals ma. I have my force. The only force that's acting here is this one because it says assume no friction. So I have my force of 30.8. I'm going to set it equal to my mass, 33 times a, and I can solve for acceleration. Acceleration is going to be 30.8 divided by 33, which is 0.93 repeating. So let's go ahead and type that in over here. Submit. Question number 6. Question number 6 says, a 30 kilogram box experiences an impulse of 30.5 Newton seconds for 2.1 seconds. So let's go ahead and see what we can label. We have a mass of 30 kilograms. We have an impulse of 30.5 Newton seconds. We have a time of 2.1 seconds. Find the acceleration, find the net force, and then find the final velocity with that other piece of information. Okay, so acceleration, I can find that if I have the same equation I used up here. I can use this to get acceleration, F equals ma, but I do need to find the force first. And that's easy enough to do because I know J equals F times T, and I have J and I have T. Okay, so again, you have to be able to see these steps, or just look at this and say, what can I find with this information? And really the only thing that's useful to you right now is this. Okay, so even if you didn't necessarily recognize that's what you needed to do first, if you just looked at this and said, I can find force, then do it, find it, and then see if that helps you to determine number 1. Okay, so let's go ahead and do that. 30.5 equals force times time. If I want to solve for force, I'm going to divide both sides by 2.1. 30.5 divided by 2.1 will give me my force, which, by the way, is this second question, so I may as well type it in here. 14.52 is going to be my force. Okay, but we can use that force, now that we have it, to find acceleration, because F net, which that is my net force, is the only force here, also equals mass times acceleration. And so I have my 14.52. I'm going to set it equal to my mass, which is 30 times a, and I can solve for acceleration if I divide both sides by 30. Okay, so I'm going to take the answer in my calculator. Rather than using the rounded one, use the one that's here. And we're going to divide that by 30. Oops. And we are going to get this as our acceleration. So let's go ahead and type that in up here. 0.484 meters per second squared. So now I have that. Let's go ahead and add it over here. Okay, and we have one more question. If the box was initially moving at 2.3 meters per second, find the final velocity. And there are a couple different ways for you to do that. I'm going to add my initial velocity though, positive 2.3. I have information, these right here, A, VI, and T, that would allow me to use a kinematic equation to find final velocity, or I know that my change in momentum is equal to mass times change in velocity, and I can find it that way. Because I already know my change in momentum is equal to my impulse, so I could plug that in. 30.5 equals my mass, 30 times, and again, delta V is VF minus VI. VI is 2.3, and so I could do it this way. So you don't have to use a kinematic equation here, although it is an option if you would like. Okay, if I want to solve this, I need to go ahead and distribute this, and I have 30 VF minus, let's do 30 times 2.3, and that's 69. Okay, so again, we're going to add 69 to both sides to get that out of here. So let's add that to 30.5. And I have 99.5. So I'm going to rewrite this over here. 99.5 equals 30 times VF. So we're going to divide both sides by 30. And we get a final velocity of 3.32 if I round that. All right, this is question number 7, and I need some more paper. All right, question 7 says, a softball with a mass of 0.24 kilograms. I'm going to go ahead and start labeling. Mass equals 0.24 kilograms. Moves at a speed of 18 meters per second. Initial velocity, 18 meters per second. The ball is then hit by a bat and rebounds in the opposite direction at a speed of 15 meters per second. When it says opposite direction, you need the opposite sign. Negative 15 meters per second. What is the change in momentum of the ball? And again, these just have opposite signs from each other. If this one's positive, this one's negative. Or if you labeled this negative, you would need to label this positive. The question doesn't actually tell us what the initial direction is. So I went with positive, but if you went with negative, it's going to accept our answer either way because there's not enough detail in the way that the question's worded. Okay, but I have these things and I want change in momentum. And again, change in momentum is equal to mass times change in velocity. Again, my change in velocity isn't 3 or negative 3 because it's not going from 18 to 15. It's going from 18 to negative 15. It's a much larger change. Okay, and so when I go to plug in my mass 0.24, my change in velocity, again, you can solve for it mathematically. VF minus VI, negative 15 minus 18. It's a much bigger change. Okay, so negative 15 minus 18 is negative 33. So that's what we're going to multiply by 0.24 to get our change in momentum, which is equal to 7.92. Again, the magnitude is. My answer that I'm getting is negative 7.92, but again, I'm telling you it will accept it either way because it didn't tell us whether this was positive or negative to begin with. So it's going to accept it either way. My units for change in momentum, kilogram, meters per second. Question number 8. Jennifer, who has a mass of 88 kilograms, is riding at 33.1 meters per second in her red sports car. There's an initial velocity, 33.1 meters per second, when she must suddenly slam on the brakes to avoid hitting a deer crossing the road. When her car strikes the deer, her forward motion is slowed by her seatbelt and the airbag. These safety features bring her body to a stop. There's my final velocity, 0. And it happens in a time of 0.33 seconds. What is the magnitude of the average force acting on her by the seatbelt and airbag? So I'm looking for force. I have mass, I have 2 velocities, so I can find change in velocity. I have time. Okay, again, my change in velocity, if I go from 33.1 to 0, is a change of negative 33.1 meters per second. So there's my delta V. If I want to solve for force, I'm going to use this formula, Ft equals m delta V. Plugging in, that's going to be force times my time of 0.33 equals my mass of 88 times my change in velocity of negative 33.1. So let's go ahead and multiply 88 times negative 33.1, and then we're going to divide it by 0.33. And we get this. So the magnitude of the force, it only wants the magnitude, so I'm going to drop the negative sign and just type it in. 8826.6 repeating, so 0.67. Again, I dropped the negative because it says magnitude of the force. My units for force are, of course, newtons. If Jennifer had not been wearing her seatbelt and not had an airbag, then the windshield would have stopped her head in 0.004 seconds. So it's giving us a new value here for the time. If that seatbelt and airbag weren't there, then now her time would have been much shorter because there's no give to a windshield. What is the force now? Okay, same question but different number here. So again, when we plug in, these numbers are the same. Okay, her mass and her change in velocity did not change. All we're looking at is, hey, if you don't have a seatbelt on and an airbag, now your impact time is a lot smaller, and when that happens, your force is going to be a lot larger. Okay, and so it's basically still going to be the same process, except it's going to be 88 times negative 33.1 divided by this. Okay, so I already have that number in here. Let's divide it by 0.004. And that's our force now. Look how much larger that number is. Let's go ahead and type it in. And again, it wants the magnitude, so 728,200 newtons. Significantly more force because she had significantly less time. All right, question number 9. We have this image here, case A, case B, same scenario with a car driving 7 meters per second. One of them bounces off of a wall, the other one crashes and stops. It says, in the figure above, the figure above depicts the before and after collision speeds of a 0.57 kilogram toy car that undergoes a head-on collision with a wall. In case A, the car bounces off of the wall. In case B, the car crumples up and sticks to the wall, which correctly describes the change in velocity experienced by the cars. Okay, well, case B, change in velocity is -7. You go from 7 to 0. That one's easy. Case A, my change in velocity is not 0.7 because it's not going from 7 to 6.3. It's going from 7 to -6.3. And so if I go to find my change in velocity here, it's -6.3 is my final velocity minus my initial velocity of 7. And it's a bigger change, 13.3 meters per second. That's the change. So that's what we're going to say for car A. Its change in velocity is -13.3 meters per second. So we have the two changes already figured out. But there's a couple statements down here that we need to look at as well. Car A experiences a greater change in velocity than car B. Yes, it does. Okay, this is a greater change in velocity. If you compare the magnitudes, 13.3 is bigger than 7. Okay, so you're going to go with that. The negative sign, again, just tells me the direction. So you're only looking at the magnitudes when you're comparing them. The next question, in which case, A or B, is the change in momentum greatest? Okay, again, you're going to have a greater change in momentum if you have a greater change in velocity. Because car A has a greater change in velocity, car A will also have a greater change in momentum. And we've talked about this before. If it bounces, it will have a greater change in momentum. It will have a greater impulse. There will be more force. Okay, assuming it happens in the same amount of time. Which describes the impulse. Again, I just said that, although there's some numbers here, but I do know that the one that bounces has more impulse. It was car A that bounced, so it's going to have more impulse than car B. But let's figure out what those impulses are. Again, impulse is equal to force times time. However, impulse is also equal to change in momentum, which is mass times change in velocity. And that's the information that we have, so that's what we need to use. So it's the same mass, 0.57, and I already found their changes in velocity. So let's go ahead and do this for each of them. So for car A, the change in momentum is going to be 0.57 times its change in velocity is -13.3. Car B is going to have a change in momentum 0.57 times its change in velocity, -7. Okay, so let's go ahead and calculate that. 0.57 times -13.3 gives me a change in momentum and thus an impulse of negative 7.581. With this one, 0.57 times negative 7, we get this, negative 3.99. Okay, so again, bouncing, sticking, bouncing or staying. Okay, so let's go back down. I already knew that A was going to be greater than B. It is. This is a larger magnitude than this. Car B does have an impulse of negative 3.99 Newton seconds. Car A has an impulse of negative 7.581. There it is. So those are the options that we want to select. Last part of this question says, which describes the force that acts upon each car? Assume the contact times in both cases is 0.5 seconds. Okay, again, I know that if I have more impulse in the same amount of time, that I'm going to have more force. So I know that the force here is greater than here. Okay, so I know car A experiences greater force, but if I want to find out how much force, I need to use this equation, J equals F times T, where these are the different values we're going to use for J. Our change in momentum is our impulse, and so we're going to have negative 7.581 equals force times, and it tells us the time is 0.5. This is going to be for A, and then for B, you're going to be using negative 3.99 equals force times the same amount of time. Okay, so in both cases, we're going to be dividing by a half, which is the same thing as multiplying by 2. So let's go ahead and do that. Divided by 0.5. Again, same thing as multiplying by 2. And then same thing here, negative 3.99 divided by 0.5. Okay, and those are our two values. So again, car A, we got 15.162, which is this value here. Car B, we got 7.98, or 8 if we round it. Question 10, and the last question on this assignment. We have two graphs that plot velocity versus time, and we have two cases where we have an object in case A that's initially traveling 10 meters per second, and then something happens, it collides with something, and now it's traveling negative 6 meters per second. So it bounces and starts going backwards. Same thing here, except the initial velocity is only 6, and its final velocity is negative 2. But in both cases, there's a collision and a change in velocity where we have it now in the opposite direction. And that's what it says. It says the graphs above show the change in velocity experienced by two 0.51 kilogram rubber balls during a head-on collision with a wall. Prior to the collision, what was the initial velocity of the ball in case A? And all you have to do is read it. Case A's initial velocity is 10. Because that's what the velocity was at the start of the graph. You're looking at the y-intercept, but it's a constant velocity of 10 meters per second for the first, it looks like 3 seconds until this collision occurs. Which correctly describes the change in velocity that occurred in each collision? Well, let's see. Case A, we start out, and I'm going to get a fresh sheet of paper. Let's find our changes in velocity. All right, so for case A, we have a final velocity of negative 6 minus our initial velocity, that's 10, that's a change of negative 16. In case B, we have a final velocity of negative 2 minus our initial velocity, which was 6, and that's a change of negative 8. Again, if you want to find change in velocity, it's final velocity minus initial velocity, and you're getting those numbers from the graph. Okay, so which correctly describes the change in velocity that occurred in each collision? Ball A's change is negative 4. No, it's not. Ball B experiences a greater change in velocity than ball A. No, A is definitely greater than B, which is what this one says. Ball A is a greater change than B. Ball B's change in velocity is negative 4. No, it's not, but it is negative 8. Let's go ahead and select that, and ball A's is negative 16. Which correctly describes each collision that occurred based on the information in the graphs? let's see, both collisions took 2 milliseconds. Let's look at the graphs. These times are in milliseconds, and it looks like this one started at 3 seconds and ended at 5. Same thing here, 3 to 5. So they do actually both take 2 milliseconds. Ball A experienced a greater acceleration than ball B. Ball A definitely has a larger change in velocity over the same time period. So yes, it does have more acceleration. And I can see that from the numbers that I got, but you can also visually see it because on a velocity time graph, acceleration is slope. And this is a much steeper slope than this. And so this is a greater acceleration than this. During the collision is where you have that, and yes, you're going to have more acceleration for A than B. They did not take 8 milliseconds. Again, the collision is just where the acceleration is occurring. Otherwise, you just have an object in motion remaining in motion. When you have that force is when you have the change in velocity. That's where you have the sloped line. Ball A experienced a greater impulse than ball B, or ball B had more impulse than A. Looking at these, the bigger impulse is going to be the one with the bigger change in velocity since they have the same mass. Again, as a reminder, change in momentum is mass times change in velocity. Change in momentum is also equal to impulse. Okay, so if you have the same mass, the one with a larger change in velocity is going to have a larger change in momentum and thus a larger impulse, and that larger change is case A. Okay, so ball A had a greater impulse. Last question, how much force did ball B experience during the collision shown for case B? So we're going to pull some numbers from case B to help us answer this. Okay, again, we already have some of the numbers up here for case B. This was our final velocity, this was our initial velocity, and that was our change in velocity. Oops, change in velocity. Okay, we have the mass of 0.51 kilograms in the question. The time of the collision from 3 to 5, the time is 2 milliseconds. And again, a millisecond is 1,000 seconds. So if you divide that by 1,000, and again, you can type it if you need to, but 2 divided by 1,000, you can, again, move the decimal if you want instead, is 0.002 seconds. All right, so let's look at the question again that we're trying to answer. How much force? Okay, so I can find force with this equation based on the information I have. F times T equals M times delta V. Okay, my force times my time, 0.002 seconds. It does need to be in seconds, so you do need to convert that. And you're not using the entire graph. You're only using where the collision occurs. The collision is just from 3 to 5 milliseconds, so the collision takes place over 2 milliseconds. Equals my mass, 0.51, times my delta V, which I found earlier to be -8. Okay, so we're going to do -8 times 0.51, and we're going to divide that by our time divided by 0.002, and we get this, -2040 as our force. And that is the last question in the assignment 502.3.